Hi, my name is Corinna Wester, and this is my video presentation for Lab 3, Magnetic Field of a Bar Magnet. So why is this important? So the skills we're working on today are working with magnetic fields, working with dipoles and how those dipoles create magnetic fields, and continuing to program in VPython. In this lab, we're looking at the form of a magnetic field and how a bar magnet, which we can treat as a dipole, will create a magnetic field, and how to find mu of a bar magnet experimentally by measuring the strength of this magnetic field at different distances. So our setup and methods, first we had to find north by calibrating our magnetometer's x component to 0. Then we needed to find the location of the magnetometer within the phone by calibrating it further. Then we set up the magnet horizontally at the end of a ruler with our phone magnetometer on top. Then we needed to find the location R where the magnetometer registered an X component of about 10 microteslus. Sorry, 1,000 microteslus. Then using this distance, we recorded the X component of the field at distances R, 1.5 of R, 1.75 of R, and 2R. Then we used these findings to find mu of the bar magnet dipole, which I'll show you on the next page. So we were given the information that the magnitude of the dipole's magnetic field equaled K into the R, and we know that K equals 4 pi over mu naught times 2 mu. And so using this, I found that mu was 7.45 times 10 to the 5th. Over here you can see my recording of all my distances and the average magnetic field at those distances, and then it computed using ln of B versus ln of R to find our K value. And so we found that the slope here is our N value, and we know that our theoretical N value should be very close to -3, so this is almost correct. And then our y-intercept here is ln of K. So the code. So for our code, we wanted to visualize the magnetic field at some different points of our bar magnet. So just quickly going through the code, here we defined the mu value that we found from the previous slide, and we defined a dipole electric field formula using a mu naught and an R vector. Here is our vectors for distances directly above, below, to the right, and to the left at a perpendicular angle with the mu vector of our dipole in our bar magnet. And here are the arrows for the two on-axis arrows on axis of the mu vector of our dipole magnet. And here is where we wanted to show an arrow at a 45-degree angle from the mu of our dipole. And we wanted to compare this from what we measured to what our formula is telling us it should be. And this is just a picture from our book, and I thought it was a good representation of what the electric field of a bar magnet is supposed to look like, so we can compare it to our final code. So here's our final code when it runs. And as you can see, the arrows on axis are straight, but then we know that the magnetic field loops around and comes back up. So it makes sense that the perpendicular axis arrows should be going the opposite direction. And the little cyan arrow is the one at 45 degrees. So for the 45-degree angle arrow, my observation at 10 centimeters away from the center of the magnet was about 49 microteslas. However, from my code, the calculated value at 10 centimeters was about 41.37 microteslas. So as you can see, these were pretty close, 41.37 versus 49. So my experimental versus calculated were pretty close to each other. So what if we had not oriented our magnetometer? Well, if we had not oriented it to the North Pole, the reason we oriented it was to get rid of the influence of the Earth's magnetic field as much as we could. So if we had not oriented it, we would have had to take into account the Earth's magnetic field, and it would have thrown our numbers off. And what if we were to stick two magnets end to end and redo the experiment? Well, if we were to stick two magnets end to end, our field would get larger and slightly stronger, however, not necessarily 2 times stronger. It would have gotten larger, so we would have had a stronger field and increased flux, but not necessarily twice as strong.